Today, if you interact with a large language model, ride in an autonomous vehicle, or search the modern web, you are running on NVIDIA hardware. They hold a valuation north of $4 trillion, and their silicon serves as the absolute bedrock of the artificial intelligence ecosystem. Looking at a monopoly of this scale, it is incredibly easy to assume it was all by design, a master plan mapped out decades in advance by corporate visionaries who saw exactly where the digital world was heading. In 1996, however, NVIDIA was an obscure, collapsing hardware startup with exactly 30 days of cash left in the bank. The company was skipping utility bills just to make payroll. Engineers were being laid off, and the remaining staff worked in an office with the lights actively dimmed to keep the electricity meters from spinning. NVIDIA's current status emerged from a series of high-stakes survival gambles made when the company was weeks away from collapse. NVIDIA's original strategy in 1995 focused on the emerging 3D PC gaming market. They secured a massive partnership with the Japanese gaming giant Sega to bundle their brand-new chip with a PC controller. This diagram shows the engineering split that nearly ended the company. NVIDIA designed their first chip, the NV1, to render graphics using quadratic surfaces, or curves. They believed this would create highly realistic visuals. The rest of the industry, however, was rendering graphics using simple triangular polygons. Then, Microsoft launched DirectX. This was a set of instructions for PC game developers dictating exactly how graphics had to be processed on Windows. Microsoft chose triangles as the industry standard, effectively outlawing the use of curves in PC games. Developers instantly abandoned NVIDIA's architecture because it was incompatible with the new Windows rules. Sega severed their partnership. Within weeks, 249,000 of the 250,000 NV1 chips they manufactured were returned as useless inventory. NVIDIA had spent their last dollars building a hardware standard that the market leader had just rendered obsolete. With bankruptcy only weeks away, CEO Jensen Huang gathered his skeleton crew of engineers. He ordered them to build a completely new, DirectX-compliant chip, and they had to do it in record time. To save their last remaining dollars, Huang made a blind gamble. In the hardware industry, the standard is to physically test silicon logic gates before mass production to avoid microscopic errors that can ruin an entire production run. Huang skipped this step, ordering the team to rely entirely on software simulations to test the chip's design. 8 weeks later, the physical chips arrived from the factory. The team loaded the untested silicon, pressed power, and it worked flawlessly. The Riva 128 rendered beautiful graphics with zero bugs, shipping 1 million units in just 4 months. This survival forced NVIDIA to adopt a permanent reliance on high-risk software simulation over slower, traditional hardware testing cycles. Now flush with cash from the Riva 128, NVIDIA stopped reacting to market standards and started dictating them. In 1999, they released the GeForce 256, creating a brand new category of hardware, the graphics processing unit. A CPU processes complex tasks methodically, one by one, but a GPU processes thousands of tiny calculations simultaneously, called parallel processing. Rendering an explosion's shadows, smoke, and shrapnel requires calculating thousands of distinct data points at the exact same moment. This led to Huang's most crucial insight. The parallel math required to render a virtual bullet or shifting light in a video game is the exact same math required to simulate physics and biology in the real world. NVIDIA shifted from building gaming tools to building hardware designed to simulate the physical properties of the real world. In 2006, NVIDIA took their second massive gamble. They sank their hard-earned profits into developing CUDA, a software platform designed to unlock the GPU so scientists and engineers could use it for general computing and complex simulations. Commercially, it was an immediate failure. CUDA was a full decade ahead of its time. NVIDIA had effectively handed supercomputer capabilities to a tech industry that was still focused on basic algorithms and simple web data. What followed was a grueling 6-year period of silence. CUDA remained an incredibly powerful, expensive tool that NVIDIA continued to fund, despite virtually zero market demand or practical application. It required significant corporate conviction to maintain a software infrastructure for a future that researchers hadn't even reached yet. That future arrived in 2012. A team of researchers, guided by Geoffrey Hinton, tried to train an artificial neural network to recognize images. They hit a bottleneck. Standard CPUs could only process a few images at a time, making it impossible to train large models. The researchers realized that neural networks function by performing millions of tiny, simultaneous mathematical adjustments. This is exactly what parallel processing is designed for. Because of the CUDA platform, they were able to use an NVIDIA GPU to process millions of images at once. Their creation, AlexNet, entered the largest global AI competition and won by an enormous margin. It provided the first real-world proof that high-volume parallel processing was the specific mathematical requirement needed to make artificial intelligence viable. The tech industry pivoted immediately. Google adapted it for search algorithms. Tesla bought in for self-driving cars. OpenAI used the exact same foundation to train the large language models that eventually became ChatGPT. The current AI revolution is the accidental byproduct of a graphics company betting its existence on a specific mathematical architecture in the 1990s, then waiting 10 years for the world to find a use for it.